Okay, so first of all, thanks to the organizers for putting this together, a very interesting mix of people and ideas. And in many of the talks, I think, especially what I heard yesterday, the foundational problems of quantum mechanics are always kind of lurking behind and sometimes come to the forefront when it comes to relativity or when it comes to the measurement problem. So what I want to do today is not enter in these discussions. Actually, I want to avoid it like the pest, because the risk is to get lost in terminology, etc., etc. Instead, I want to indicate to you that there exists an interpretation of quantum mechanics which is basically outside of the classical set of interpretations, and which has been proposed and pushed in recent years very much by Gerard. And I cannot do more than just indicate that it exists to you, but maybe you get curious and look at the papers later. Then I want to use this and work out a simple model according to this interpretation. And finally, this is addressing the context of the meeting, I want to try to draw some really naive or simple-minded conclusions with respect to the possible existence of quantum classical hybrids according to this interpretation. So let's go in. I hope I manage the technology. Okay, so here is a menu of what this interpretation is built on. The idea is that there are ontological states, which are the physical states, a finite deterministic universe, if you want, a finite deterministic system can be. And we denote them with this ket notation. Crucial is that there exists no superpositions of such ontological states. This is crucial, crucial distinction from quantum mechanics. And therefore, this is kind of connected, actually is kind of a consequence that these states evolve by permutations among themselves. Let me see, I can use the cursor. So like indicated here, this is just to give you something to look at. Then we can declare this selected set of states, which is, let's say, is given once and for all. We can declare it to be an orthonormal basis set. And from that, we can go on mathematically. I mean, we just do then mathematics to define a Hilbert space, and then we get an interpretation of these labels of the states, etc. Quantum states or quantum superpositions then are formed by superpositions in the usual state of these once and for all fixed basis states with some amplitudes. Then, taking into account this evolution or dynamics by permutations, we see immediately what happens if such a state is evolved. It evolves in such a way according to this, what I gave here as an example, according to these mappings of the states, and the amplitudes do not change. That means the amplitudes are actually fixed by the initial state. Again, this is a distinction from quantum mechanics, you should notice, and Hooft refers to this as the conservation of ontology. From there on, you can reconstruct, in a sense, the whole machinery of quantum mechanics. It fits in this picture. Of course, it is different, but the main point is that quantum mechanics is viewed as a mathematical device to describe a situation as listed here. Then there are, of course, problems. Otherwise, this would be widely known by now. Namely, we have, for example, no description of the standard model except massless neutrinos, which can be fit into this picture. Also, I should say the quantum harmonic oscillator can be perfectly described in this context. Maybe later I will say a little bit more about this if time permits. The difficulty which arises to start with such an ontological model is to introduce interactions. That is not trivial, and we will see some steps in this direction later. Then, oops, what did I do? Oops. So let me skip this. The main positive, or should I say, the main supporting point of this interpretation is that there is no collapse problem. There is no measurement problem from the outset. So this is something very strong, and I don't want to even try to explain it here, but for me it's a very convincing point of this interpretation. And you find other questions which immediately arise with respect to Bell's inequality, free will, etc., you find extensively discussed in Hooft's book. So this is absolutely impossible to get into here. Now, instead, I want to do something concrete. Let's assume, to describe this permutation dynamics, let's assume we have a set of n objects, or which I call these ontological states, and they're mapped into each other involving all states by permutations. Then there is a standard ordering of these states, which are referred to as a standard basis. And on that standard basis, these permutations can be represented in the form of an n by n unitary matrix, which has this form. The phases which appear here later, I will just set them to 0 because for today they don't play any role. They're completely passive. They're there, but we don't need them and they don't do any harm, so we can set them to 0 later. A crucial observation is that these permutation matrices have the property that if you take the nth power of them, you basically reproduce the unit operator. And that tells you the Hamiltonian, which is connected to such a unitary in the usual way, which is just a definition of the Hamiltonian, if you wish, that the eigenvalues of these Hamiltonians are just roots of 1. So we can easily write down the Hamiltonian in the diagonal representation. And the eigenvalues are these. Here are still the phases. From now on, I will drop them. And this is the diagonal basis. Then a little thought tells you that the diagonal basis to this standard basis, which is in some sense the more physical one, because it tells you how the ontological states one goes to the other in a very simple way. They are related by discrete Fourier transforms, and you can undo it to find the Hamiltonian for the original basis of the ontological states, and you find this kind of Hamiltonian. Now this Hamiltonian, this type of systems, has been called a cogwheel model because it describes basically, if you want to picture it, the jumping of a point on a circle in discrete steps with constant velocity. So this we will later use. This is just a tool. It's the simplest example, and we will use this later to analyze a more interesting physical model. And this is what I will get into now. Let's consider a classical spin chain, a chain of Ising spins, which can be either up or down, like here. And we have 2 times s of such spins. You can say we have 2s plus 1, but the last one is identified with the first one, so we have periodic boundary conditions. Then in order to go towards dynamics, we have to somehow introduce permutations of such classical spins. This is written here. And the notation is such that this SI is the value of the spin at the i's position along the chain. Okay, so the permutation, the transposition exchange just switches these 2 spins or the values of these 2 spins. Here's again this periodic boundary condition. And the properties of these exchange operators you probably know from quantum mechanics course. They can be written in terms of Pauli matrices. This will be very important for my argument later on. This rotationally invariant coupling of the Pauli matrices. And we can now define the dynamics of our chain in a very particular way. We choose it. I mean, we choose it and we see what will happen. So the dynamics is given by a unitary operator, as I told you before. It's a permutation operator. And from this, we want to learn what is the Hamiltonian for this Ising spin chain. It's all classical deterministic evolution of these ontological states, which are described by the classical Ising spins, these 2-state spins. There's no Hilbert space here. Okay, and we distinguish these permutations, just to give a name, according to whether the first index is even or odd. We distinguish them, these pairs of spins, which are exchanged with this permutation operator, we call them even or odd pairs, just to give a name. Okay, so, and now our task is to extract the Hamiltonian from this ansatz, if you wish, for this unitary operator. Why did I do this separation into even and odd pairs? So first, all the even pairs are updated. This works on the state of the spins, this last one first, and so on and so forth. So I work along this line. And why did I separate them? Because this is very important. We don't want that if you touch this Ising spin change in one point, you immediately, in one update, which is this time scale t, which comes into it, that in one time step, you feel the effect of touching this the chain in one point. You don't want it to arise everywhere else on the chain in one time step. So we want to have, because if the chain gets bigger and bigger, this would signify that we have an infinite signal velocity. This we don't want, because this will be much more difficult to repair later if we have more complicated models. So it's better to build it in from the beginning. Then there are a number of conservation laws of this evolution operator, which I don't want to show you here. They're in the paper. But the effect of this is that the dynamics is very simple. And I try to illustrate this here in this little drawing. Here's the initial state on the lower line, and the first updated state is on the second line. And I distinguished here full blobs. These are the even sides on the chain, and the open dots are the odd sides. And then what one finds, a general state is given like this. So the first spin has value as 1, and so on and so forth. And what this operation here does, it moves the spins, or the value of the spin on the odd sides, to the next odd side to the left. So it's a very simple dynamics which is encoded in this, and it moves the spins on the even sides to the first available side to the right. So if you look at it, it looks extremely simple. We have these left and right movers, which is actually kind of reflecting this separation into pairs. You can say these are sort of primitive light cones here. And the property of this is, if you think about it, how many updates of this kind you need in order to go through the chain once. You need exactly S updates. So in a way, we have such a cogwheel model again, as I described in the beginning, where we extracted the Hamiltonian. The only thing is that we have a large number of such cogwheels, each red arrow, so to speak, which continues in the next update to here and to here and to here, and eventually comes back to the beginning here. Each one is a cogwheel, and they're kind of composed together in a very particular way. So what do we do with the Hamiltonian? How do we get the Hamiltonian of this? We still don't know this. Because we recognize that it is such a cogwheel model, what we have to do is we have to trace this cogwheel model, which I discussed in the beginning, which was, so to speak, the rudimentary form of it, which was this one, the Hamiltonian giving here, the matrix elements of the Hamiltonian. We have to kind of trace these terms here in a suitable way so that they act on these Ising spins in the same way as this original cogwheel acted on the points on the circle, so to speak. And this can be done, the details you find, this is the paper I'm referring to, you find there. And what comes out is this Hamiltonian. Again, I want to emphasize that this is classical again, in the sense that this Hamiltonian, when put into the exponential, produces exactly the updating rule which I described. So it's completely classical, deterministic evolution. Is just a slightly more complicated model than this original cogwheel. It's this Ising spin chain. Okay, so now, if you look at it for a while, this operator is actually very close to quantum mechanical operator. In fact, it is infinitesimally close to quantum mechanical operator, despite the fact that it comes from this classical deterministic dynamics. First of all, you see that it has no free parameters except the size of the chain and the time scale, which defines, so to speak, the energy scale of the Hamiltonian, or the time scale for the update of this spin chain. And then we recall that the Hamiltonian is essentially related to the logarithm of this unitary, and the unitary is given in terms of these permutation operators. So now if we put this back into here, and the Hamiltonian into the exponential, then you find an interesting sort of Baker-Campbell-Hausdorff formula, because these operators are trivial to exponentiate. And what is interesting about this formula is that it's a terminating Baker-Campbell-Hausdorff formula. There are not infinite many terms arising here, and there are only very few Baker-Campbell-Hausdorff formula of this kind are known. I mean, for very simple operators, you can do that. In general, this is an infinite series expansion, but here it comes out because of this simple dynamics. It comes out in this cute form, and you can see the details in the paper. But now I want to use this result for something else. Namely, I want to point out that if we have small errors in this Hamiltonian, let's assume we live in a fictitious world where we don't know yet what our Hamiltonian is. We know some terms maybe, but we don't know exactly the coefficients here, or we don't know all terms. Any kind of approximation or perturbation of this Hamiltonian now has actually, with respect to the ontological dynamics, has a disastrous effect, because it turns immediately this classical dynamics into quantum mechanical dynamics. And this is what I want to, the kind of argument I want to present here using this simple model. So let's think of a long chain, very large, and take only the leading terms, the two leading terms here from this sum. Let's assume we don't know.
Else you have 15 minutes.
Okay, I think I will manage. I'm rushing very much because I'm always afraid to go over time. So I will manage, there's no problem. So we take the leading terms of this to illustrate the point, okay? And then if you look at this Hamiltonian, the leading terms are this, then this immediately, because of the sum of terms, generates superpositions. That means if we start with such a state of this Ising spin chain, instead of going back to a state of the Ising spin chain, we introduce superpositions, which by definition do not belong to the ontological states with which we want to work or with which we started. And we can say in words, just to phrase it, that any perturbation of this Hamiltonian, this deceptively simple Hamiltonian, any perturbation or mistake which we make here because we don't know better, let's assume that, any such perturbation opens basically this space of multiple two-state spins, excuse me, opens it to a Hilbert space. So we can say what we get are, so to speak, qubits by mistake. And let me make this a little bit more clear. So here's again what I want to take as an example. And let's assume that the initial state on which we apply this Hamiltonian is like this. All the spins in the classical spins in the chain are up except two spins on neighboring even and odd sides. So this is what I indicated here. Then what this thing does, it moves by this permutation dynamics, it moves these spins to other positions. For example, let me see, what did I do? No, exactly, I'm sorry, what I'm saying. Yes, it moves this down spin to here and it moves this down spin to here. But because there is a second term, you get also contribution where this spin is moved a little bit further and this is moved a little bit further. So this is now interesting. By the way, I should say I did not care here about normalization and any constant factors. I just dropped everything to concentrate on the essential aspect of this, because otherwise the slides will never fit for me. Okay, and what you see here was kind of interesting. If you look at this combination here, you have an up, a down up spin, an up down spin, and here again you have the opposite, a down up spin and an up down spin. This reminds you of a Bell state, except that it appears in two places, this kind of typical combination of a Bell state, and clearly this is not an ontological state. Now this observation, very simple, really naive, what is immediate consequence of this ontological dynamics, I want to use this to say something about quantum classical hybrids in this picture, okay? In this interpretation or in this picture that we have ontological states evolving by permutations. So let's assume now that instead of one chain, we have two chains. One is denoted by psi and one is denoted by the primed quantities. So the spins in this classical chain here have the values S2, 3, and so on. And the last one is identical to the first one with periodic boundary conditions. Similarly, the second chain have these values. And this value, this state of affairs for these two chains, if there's no interaction, is arrived at by one update from a previous state according to this unitary, which I discussed, this complicated, slightly more complicated permutation operator. Now, however, if I make a mistake in this unitary, as I explained on the previous slide, namely that the Hamiltonian which goes into it has a slight mistake, or we don't know all the terms or something of this sort, let's assume that this one here is arrived at, this value is arrived at by this mistaken Hamiltonian. Instead, this one is arrived at by the correct ontological Hamiltonian. Then this state, which has this mistake built in, actually comes from a state which has this form. It has this superposition built in, which I discussed before when I discussed the effect of this perturbed Hamiltonian. So it has a superposition built in. So I give it an index QM for quantum mechanical. And I have now a simple possibility to look at a quantum classical hybrid, namely I keep one according to the ontological dynamics and properties, and the other one with this mistake built in that it has a superposition built in, okay? And now nothing would be interesting if there was not an interaction between the two chains. And I take the simplest possibility. I want to have an interaction between these two chains, which again maps ontological states on ontological states. That means Ising spins onto Ising spins without it doing anything, a linear map which does this. And I'll show you an example, which is this one. I choose a very simple example here. And if I do the updating correctly, what happens is that here I have cut out a piece from one chain and cut out a piece of the other chain just to make it visible. What this interaction does, it takes two spins here and puts their values into the other chain with order interchanged. And similarly, for the other chain, it puts these two values to here with the order interchange. So it's like a simple scattering between two Ising spin chains with this effect. I just choose this as an illustration. It has no deep meaning. It's just to illustrate, and any more complicated choice will produce similar effects, of course, I mean, except much more complicated. But then this, what comes out here from this interaction, if I do everything correct, is still an ontological state. Now, instead, if I do, as I said on the previous slide, I assume that this state here, this chain here, has this mistake built into the Hamiltonian. So I give it again, I replace the correct ontological thing by the quantum mechanical thing. And what I have is a quantum classical hybrid. Now we have a quantum mechanical factor with a superposition built in, and I have an ontological factor, just these Ising spins without anything else. And now I apply this interaction. What comes out is you do the little calculation. You get something which looks like what you would get if everything was correct. There was no mistake in the Hamiltonian, but again, you get an additional piece. And as I said before, I don't care here about normalization factors and the correction terms which are missing because, or which would be there if I had other contributions to the Hamiltonian here on this part, etc., etc. So there are always, you can add other things. And this then is what I wanted to show you, that just let me say it again. I have these two classical chains or ontological chains of Ising spins. They interact with each other. In one chain, I propagate this chain with a slight mistake of the ontological Hamiltonian. And what the result of it is that I get a superposition in the final result of this interaction, which kind of transports this superposition, not only from one factor with which I started, where is it? Here. It is not confined to this factor with which I started, but it goes over to both. So the quantum mechanical aspect is kind of infected to the whole system of two chains. And this was the thing I wanted to tell you, that the system does not remain in the correct space of ontological states with which I started. Instead, if you make mistakes in the evolution, you get this quantum mechanical aspect and everything becomes quantum mechanical immediately. Of course, this is a primitive model, but I think every more complicated model built along these lines would show this effect. I mean, this is of course speculation, but it's very likely, and what goes in basically is the linearity of the whole evolution in some sense. So let me summarize this for you. What I try to indicate, I cannot really do justice to this at all, is that the cellular automaton interpretation of quantum mechanics, which is based on the evolution of states by permutations, nothing else but permutations, is generated by a fine-tuned self-adjoint Hamiltonian. There are no free parameters except the size of the system in this example and the parameter which tells you how long does it take to do one update. And then I showed you that any inaccuracy in the Hamiltonian induces an enlarged state space. Namely, you have to allow for superpositions of ontological states. So you immediately go out and you go into something which we know every day from quantum mechanics, okay? And then the final part of the argument was to look at the consequence for a simple quantum classical hybrid in this way. And what I find is that any interaction, I mean, I gave the most simple that came to my mind, but you can make it more complicated. Any interaction will transfer the quantumness, the quantum aspect, namely that we have superpositions there or even entanglement, as I showed you, will transfer these aspects directly to the complete system, which in my case consisted of two chains. So here I think I'm finished, and I thank you for your attention. I hope it's not too confusing. And here's a list of references which I actually wanted to comment something, but time is up, and let it be as it is. Thank you.
Thank you for your talk. Danielle and Guy, you can ask first.
Hello, Thomas. This is Daniel Sudarski. Sorry, the
Yes,
name.
unfortunately, I don't see you. It would be nice to see you.
Okay. I'm still in my pajamas in Mexico. Sorry.
Oh, okay. Next time we make a fashion show. Okay, tell me.
Next time. Okay, I wanted to make a few comments and then ask a question. Well, as you probably are well aware of, this proposal of this general idea has been strongly, criticized in connection with the issue that you mentioned, violations of Bell's inequalities. As you probably know, there has been a long debate between Hooft and Tim Motley in the blogs regarding the path that Hooft has chosen to evade the consequences of Bell's theorem, which is basically what is called settings independence, or in other words, what he wants to remove from the world in order to avoid Bell's theorem is what he wants to put in is something called superdeterminism. And it has been argued that superdeterminism, that philosophical position, would basically void the possibility of even doing science, any kind of science, right? Because if everything is determined to minute detail from the beginning of the world, and all sorts of correlations exist between all these fundamental underlying these cells in the cellular automatons, then you could and then you could not rely on statistical trials, for instance, of vaccines to decide if these are good vaccines, or simply they happen to be set up from the beginning of the universe, that the people that received the vaccines happen to had a better immune system and cure themselves, or things of that sort. Well, that's a comment. We have actually recently wrote a paper showing a precise model containing these features of violations of settings independence, and show that the problems that you have to pay if you try to do really concrete global models, not models of a specific experiment, but global models of the universe that run on that idea. I will put it here for, in the chat if somebody wants to read it. But what puzzled me in your presentation is this issue of mistakes contributing to change what was, our knowledge or our prediction of the state to actual ontological states, changing what actually happens in the world and not just our predictions. So this, when you had these two states, one is what is really going on in the world, which I suppose that's what you mean by the ontological states, and something else, which is our own mistaken calculation of what goes on in the world that appears because we have mistakes or we don't exactly know what was on in the world. And you mixing these two things up, right? Mixing these two things up, and now providing the full combination to ontological sense. So that seems to imply that, in a sense, what we know or don't know about the world happens to influence the things that go on in the world.
No. So, that part is not so. The world, in quotation marks or whatever the object is, evolves ontologically and keeps doing that all the time.
Right.
The problem comes in when we describe it, and since we don't know how to do better, we describe it at a certain point. We are forced to describe it by quantum mechanics, as I said.
Right.
Because if we do a mistake in the Hamiltonian, this immediately puts us out of this ontological state space. It introduces superpositions, or even worse things like entangled states.
Right. It introduces superpositions in our description, but not in the world.
Yes.
There are no superpositions in the world. These just happen to be in our descriptions. And these superpositions,
exactly.
Nevertheless, they create these mysterious correlations that we see that we do see in the world. That
in our description of
in our world, Bell's inequalities have been tested, with things in the world, and it's not just that we see them; it's that they are there. These things are occurring in the world, and the tests are every day more sophisticated and every day more complex. So the question is, why would on earth a mistake that I make in my description be confused with, strong correlations that we do see in the world?
According to how I understand Hooft, I mean, he's not responsible for my misunderstanding. These correlations which we see are interpreted or extracted from experiment according to our poor means of doing that, and this poor means is quantum mechanics. So we just cannot avoid that.
No, we do measurements.
We don't see what the ontological states do.
Right.
At least
but
not until we have a good idea.
But independent of what the ontological states Bell's inequalities should hold, what you have is some kind of hidden variable theories, local and presumably local hidden variable theories, and Bell's theorem has been constructed for that and cover all of that.
That's exactly the discussion I wanted to avoid.
Maybe we can continue the discussion. Maybe we can continue the discussion in lunch break. Let's just move on. Thanks for your question, Daniel. Let's just move on to Dio's question.
Thomas, I loved your talk to the extent that I would love to translate it into my completely ontology-free terms of into my ontology-free terms in my vocabulary. So my usual vocabulary doesn't contain terms like philosophy and ontology, and I would like to translate next time, not in this short time, next time, or in a letter to you. So I would love to translate it into my more Earth-based language.
I think just a quick reply. I think a good starting point would actually be your book, where you parallel the classical and quantum mechanics on the basis of density operators and all this. And I think that would be the right way to put these things together. I mean, here on the one side, classical in quotation marks, the ontological side, and quantum mechanics as usual. I think that, yeah, there is a whole program, certainly.
I will send you a message.
Good.
Email, yeah.
Okay, very good. So let's see what the question from Benito. Can I ask your question?
Hi, thank you very much for the talk. Can you hear me?
Yes.
Yes.
Okay, so my question is much more, I guess it's more concrete. I wanted to understand, for example, so one of the things in, let's say, Copenhagen or standard quantum mechanics that we do is do these projections when we measure. So,
yes.
For instance, in this spin chain model that you have, so suppose that you have the wrong description that looks like quantum mechanics, and that we perform a measurement, you know, from our ignorant point of view, we perform a measurement in this setting, and this will cause the state to project, you know, according to the standard rules. And how does this translate? I mean, this will happen in the fake picture of the universe and the ontological.
Yes, exactly.
And is it so that when I make a measurement, do I then again get closer to the real description of the universe, or not necessarily so? I mean, how does this work?
That's a good question. I mean, the last question, I don't know the answer whether we would get closer. The hope is we would, but this is difficult. But I wanted to answer to the first part which you asked, which is very good. Let me try to just jump back very quickly. Here, I think here I said that basically I skipped over this very quickly because I did not really say what in connection with quantum states, what the usual classical states are. The classical states in this picture are probabilistic distributions of ontological states. And this reflects to the fact that if we would know a little bit more about the system and some of the ontological states and could do something like experiments, then different initial conditions in the experiments, because we cannot reproduce it perfectly, never, because the ontological dynamic runs its way whether we do or not. I mean, there is of course a big philosophical question here. What are we in this picture? And Hooft does not answer to that as far as I understood him. There is no answer. What is the human being, or the famous PhD student of Bell who comes into the picture and finally talks about it? So that part is not addressed, and I have nothing to add to this. But the point is that the ontological dynamics runs its way, but we admittedly don't access it perfectly, or not even vaguely. So different experiments which we see or which we try to describe reflect different initial conditions, and then the quantum superpositions which describe the ontological states in our language, in our mathematical language, they have to collapse, because the real dynamics never collapses. The real dynamics just goes from one state to the other, like I said here. I mean, it goes like this goes to this. I mean, just an example here. This goes to this, and the amplitudes are fixed once and for all by the probabilities which come in by choosing an initial state. So I don't know whether this really answers your question, but
and I guess from your
explanation, the point is that there is no collapse. The collapse is in the mathematical description. That is what the statement is. And of course, I mean, many people don't like this. And as the previous question by Daniel was, that there is a heated debate going on about this, and people really accuse Hooft very harshly. I mean, they say it's completely crackpot. but but I think it's worth trying because it's so elegant and simple, the basic idea. It's worth trying. And what is really needed is to do some work to find some models which take us closer to the real world, in the sense, for example, to formulate such a spin chain or something like this, which also has interactions, let's say, of gauge forces type. Then suddenly I think many people would start to look at it much more carefully. Until now, we have only harmonic oscillators or this Ising spin chain, which are presented now. And the next step will be, I mean, to make this Ising spin chain, the spins among themselves interacting and things like that. So it's a very slow and long process, but I find it fascinating and worth trying. I mean, I have nothing to lose and it entertains me.
So just to make a remark from you, from the explanation that you just gave me, you know, just reaffirming what you said in your talk, but now it kind of, I got it better in my brain maybe. Is this, I mean, it is more or less in the same spirit as a kind of Bohmian mechanics, where there's a reality out there, there is some real, you know, observables that we cannot access. Well, except in that case, it's observables, but in this case, it's states maybe. And then we interpret some stuff partially in terms of the wave function of quantum theory, and this is, and we can access some information of the real world, but we can never know it, the whole picture. I mean, is it in the same spirit?
It's an interesting question. I have not thought about this, but of course one could try to match such a, in particular, discrete dynamics on a discretized version of Bohmian dynamics, some simple models, and see what it looks like, whether there is a closer connection to what I was talking about here. I have not thought about it, and I have not heard about it from somebody else either. So that's an interesting question, actually. I don't know. I mean, I personally never looked into Bohmian mechanics because it somehow, the fact that we still need the wave function doesn't do any good. I mean, if we want to do something better or not better, let's say quantum mechanics is the best we possibly can have. But if we want to do something which explains to us humans quantum mechanics in a better way, then we better do something which goes beyond the wave function. We should know what the wave function means. I mean, what is it? What are we talking about? Is it just mathematical apparatus, as in this context, as I presented here, or is there something else there? I mean, there are also big debates, I mean, independently of these Hooft ideas, on the status of the wave function. I mean, you find all kinds of ideas, and there's nothing decided yet.
Okay, thank you.
Okay.
That was helpful.